Okay, so I'm not going to talk about parallel SystemC today. I'm going to talk about parallel programming on top of SystemC, which makes a small difference, which is I'm describing an approach which doesn't modify SystemC here. So, okay, the standard copyright permission. The two main questions, there are so many of them. The two main questions raised by parallel SystemC is when can I parallelize? Which process are candidate for parallelization? And then the SystemC standard says you have coroutine semantics, which essentially means you need to be sequential, and we still want to be parallel in terms of execution with the semantics, which looks like coroutine. So the classical answer to the first question, which process can we run in parallel, is when they have the same simulation time, the normal SystemC will run them in sequence, but somehow they are executed at the same time simulation-wise. So it's quite natural to run them in parallel. But then obviously it raises the question how to ensure coroutine semantics even when you do that. The second question will be addressed more by the next talks about scale and risk. And by the way, I'm also a co-supervisor of the PhD behind scale. So I'm not the speaker, but I know the subject also. And in this talk, I'll focus more on the first aspect, which process can we run in parallel? And my claim is that in many cases, just saying same simulated time implies parallelism is not sufficient because there's just not enough parallelism potential. So the idea that I'm going to talk about in this talk is we need something more. We need to let the programmer express two things: how to desynchronize threads to allow more potential parallelism, and then how to resynchronize stuff, because somehow coroutine semantics is very convenient. And I don't think you want to make a parallel platform using just threads and mutex with the basic parallel semantics. So I'll start with bad news. This is a measurement that we did with ST Microelectronics with Jérôme Cornet and Laurent Maillet-Contos on a real platform. What we did is to measure how many SystemC threads, SC thread and SC method, are eligible in the same delta cycle. So somehow this is what is the potential for parallelism if we just rely on an approach which says run in parallel stuff that are at the same simulated instant. And depending on the use case, well, sometimes it's just one process almost all the time. I'm trying to be clever, but it doesn't work. I wanted to draw on my slides. In some cases, it can be 2 or sometimes 3, but it's very rare in this platform to have more than 3 processes eligible at the same time, which means fundamentally you cannot make more than 3 times acceleration, and most likely this is going to be 1.5 or maybe 2x acceleration, which is a nice to have. But I mean, we have so much potential for parallelism in the host platform these days that it's quite clear that we should be able to do better. Okay, and I don't know what I did, but apparently I've lost my pointer. Okay, I'm back. So the idea behind the two less durings that I'm going to talk about here is we'll keep a SystemC platform as usual with threads, as SystemC threads with normal SystemC semantics. But sometimes there's a computation that you want to offload to something else. You want to delegate it to another thread. And on the right-hand side here, we have different operating system threads, P threads in Unix, which are going to run in parallel with the platform. So the idea is quite simple, as is. It's quite standard in parallelization. I have something that is costly. I'm going to parallelize it somewhere else. But the idea is to try to do it with reasonable semantics and to be able to fall back on SystemC semantics whenever it's needed. The nice thing is I don't need to modify SystemC. It's really, I need something to start a task that will run outside SystemC, to interact between SystemC and the outside task, but I'm not modifying at all the SystemC kernel here. Which means that if your SystemC here is already parallel, you can do both and use a parallel SystemC with some other task on which you can delegate some other computations. And we need some weak synchronization between SystemC and the other tasks. I don't want to say this is parallel, but it has to finish before the end of the delta cycle, because otherwise I know that I'm going to have my outside task run for a while, but SystemC will be blocked during that time. So I really want to be able to say, start the task, but do your stuff for a while, and we'll synchronize afterwards late enough that the synchronization is not costly. And the key idea behind that is the notion of task with a duration. In SystemC, usually stuff for instantaneous. You say, I'm doing a computation, and all the computation is done in 0 time in terms of simulated time. And here I want to allow the fact that this computation takes time. I know when it starts, I know when it ends, but I don't want to know what happens in between. And this is left to the operating system scheduler to decide. In terms of timing diagram, the typical SystemC is on the top here. You can do a computation. So F here, so let's try again. Yeah, F here is instantaneous. And computation are done in 0 time. And what I have also is intervals of time where nothing happens. So either the computation is instantaneous or intervals of time are just empty in terms of computation. And what I want to do with the scheduling is the exact opposite. I want to know that it starts here, it ends here, and the computation is somewhere in between. But maybe it's going to be here, maybe it's going to be here. I leave it up to the operating system to decide. The computation will just run without synchronization between the start and the end of the task. So what this is pseudo syntax, but essentially you're going to say during 15 units of time, execute computation H, instead of saying H with the wait statement afterwards. Obviously, I can have several tasks with duration. And the parallelism here is can be between H here and this task, because this happens between the beginning and the end. And here also I have an overlap between H and J. So I allow parallelism between H and J, which would not exist if H and J were instantaneous at the beginning or at the end, for example. It's very simple, actually, to implement this idea. You can do that in 3 lines of code, and the code at the top is not even pseudocode, it's actual code that works. You can execute it, and it does what it claims to do. It's just quite inefficient, but it still works. The function during here, it starts a new operating system thread, sorry, using basic C++ standard construct. So I'm starting a thread executing F. Then I'm waiting, and you have to remember here that wait is SystemC wait, so it doesn't block the whole process. It blocks the SystemC process, and it context switches to other threads. So what happens, one here creates the thread, and because I'm context switching to other threads, the wait statement context switch to B, for example, or A at the top here, 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 and so on. And at the end of the task, I'm just calling join. In case I'm lucky and F was fast enough, maybe it's already done and join is non-blocking. And join can be blocking if the computation in F took more than D units of time in terms of simulated time. So, okay, end of talk. I'm done. 3 lines of code. Not really. We need more. Well, first, is it enough? Do we just need that notion of task with duration and be done with it? It's kind of fork join. I have the fork at the beginning of the task and the join at the end. And my claim is that sometimes actually it can be sufficient. There are typical patterns of code that you can find in many platforms, which are, I'm doing a big computation, and then I'm saying how long it took. And because there's no way in SystemC to say it took 10 units of time inside the computation, the simplest is to use the wait statement afterwards. And if you just replace that with a simple construct during 10 milliseconds, do some big computation. If the computation doesn't interact with the SystemC simulation, you have this very small modification, and you get a good acceleration factor if your profiler told you that big computation here was actually a big computation. So it doesn't solve all the problems, but this very simple construct already solves some real problem if your platform looks like this. Obviously, sometimes it doesn't. Sometimes it's not just for join synchronization. You need some time synchronization because maybe the task is not just a beginning and an end, but you want to have control on how much decoupling of time you allow between the task and SystemC. And sometimes also you want the task with duration to interact with the scheduler. Typically, maybe you want the task with duration to do event.notify, and this is forbidden because you are in an external thread. So you cannot access the internal SystemC kernel data structure without some kind of locking mechanism or so. And the idea here is to provide something a bit higher level than just locking with mutex or things like that. About time synchronization, I have two extra constructs. Extra time of t, it can be used to increase the duration of a task. So you start with a task that has a given duration here. And when you say extra time of t, you just increase the potential duration of the task. This is typically used for a task which cannot be predicted in the beginning. You start a task, but you don't know how long the computation will take. You can start with pessimistic duration, and you can increase the duration as the computation progresses. And if you use extra time quickly enough, you don't have to pay a costly synchronization because you know that your horizon of time will always be ahead of you, so you can still run without synchronization. But sometimes, well, and yeah, I was about to forget, the other possibility is that the task can be unbounded. If you call extra time in a loop, then you can just start a task with duration, which has an end, which is just a temporary horizon of time, and you can let the horizon of time grow indefinitely. So for example, in the paper about ST-during, I have an example, which is an ISS, which is delegated to a separate during task. And the ISS doesn't execute for a while and stop. It executes in an infinite loop, but I'm calling extra time in this infinite loop, so I let time elapse, and the ISS is slightly temporarily decoupled from SystemC simulation. And the opposite of that is if you call extra time too much, then you allow a lot of freedom. You say, I'm allowed to execute until simulation time very far in the future. But sometimes you want to actually execute at that point in the future. And this is what catch-up does. It just says, I'm blocking until SystemC time actually reaches the current time of the end of the task. And to give a bit more flexibility, I have actually a timing parameter here to say plus minus t to let a bit more chance of having a non-blocking synchronization. So with this, you can say how much SystemC can be ahead of you, and you can force the timing synchronization between the task and SystemC. Okay, if you want to look at the actual implementation, but I'm not going to detail it, you have the slides offline. And this allows actually to do something very similar to temporal decoupling. I have here on the left-hand side a basic temporal decoupling where I have a local clock T-local, which I increment from time to time to reflect the amount of time of computation of F, G, and so on. And sometimes you say, okay, I have a temporarily decoupled simulation. My local time says I'm at t equal to 20, but the SystemC time is still 10. I want to resynchronize with SystemC, and then you call wait, and you reset your local clock. So usually you do that with the higher level API, but the underlying mechanism is this one. And it is more or less equivalent to saying inside an ST-during task, I'm doing F, extra time of the amount of time needed by F, extra time, and so on. And it lets the task grow. And catch-up is somehow the equivalent of wait and reset my local clock, because just after catch-up, I know that my SystemC time will be the same as the ST-during task. So this is for time synchronization. And so my claim is that you can have a coding style which looks a lot like temporally decoupled simulation, but use that to get efficient parallelism. And what I'm going to talk in this slide is scall, which is how to have a task interact with SystemC without having actual concurrency. So fall back to SystemC semantics on coroutine semantic for a while. What you're not allowed to do is calling I++ or calling I.notify in an SC during task, because it would really be a race condition. But what I'm allowing with SystemC is SC call of some function. So this is the C++ syntax for lambda, if you don't know it. This is just a bug. I forgot to remove that quote. And I'm just executing this piece of code in the context of SystemC. So the task just sends back a piece of code to SystemC, which executes it, and the e.notify will be executed in SystemC semantics. So the way it works, I'm not going to talk about all the coding detail and so on, but essentially you start with the task, and when you launch SC call, it sends back a function pointer to the calling thread here. I'm using the asynchronous request update mechanism here to trigger an event in SystemC and execute the function. And okay, this is the pseudocode that you can have a look at offline. So I lied when I said that the 3 lines of code were enough. First, you need the extra time and so on, extra primitives. And for efficiency, starting a new operating system thread with a new OS call at every time is very costly. So I have quite basic way to manage threads in a much more efficient way. So I have thread pooling here, where I pre-allocate a set of threads, and instead of destroying them, I just block them on a condition variable. I also have a sequential implementation, which is just a reference, which is very simple. And this one is essentially the 3 lines of code that I showed you, plus the mechanism needed for SC call and so on. Benchmarks. So this was on the 48 cores machine. That was a long time ago. I didn't have the occasion to rerun the benchmark on a more recent machine. What we can see is that we have a quite good speed up for loose timing platforms, and this was really my target. Clearly, for fine-grained synchronization, the performances are quite bad. The scaling factor is a bit limited. One reason for that is that I wanted to avoid polling and so on. All the primitives that block a task are always on an explicit mutex lock or condition variable. I know that this is nice for other users of the same machine if this is a shared machine. I also know that there's a potential benefit by using atomic operation and polling and so on. But this is not done, so most likely you could have a better speed up here with atomic operations. Okay, so the conclusion on SC during, this is a new way to express concurrency in the platform, especially targeted on the notion of duration instead of instantaneity. It allows parallel execution, and it's really targeted on loosely timed platform where we don't have clocks and so on. I don't modify SystemC, so it can be used on top of a parallel SystemC kernel. And I already talked about the potential performance improvement. And we're here to talk about potential evolution for the standard. So there's a very simple answer, nothing. It already works. SC during works without modification, neither of the standard nor of the implementation. On my wish list, I still know that I could implement SC call in a bit better way. Currently, I need to call an asynchronous request update, which notifies an event, which triggers a thread. It's an implementation detail. It could be slightly better. But more generally, what I think is SC during is a nice library, but the ideas inside SC during could be used. And I really think that the notion of exploiting temporal decoupling in the way we parallelize the platform is an important idea. I don't know if SC during is really the solution, but I think this particular idea deserves to be present at least in the discussions. And that is the end of my talk, and I hope you have a lot of questions, and I want to thank you for your attention.
Thanks a lot, Mathieu. Very good. We are actually on time for the next presentation, so perhaps we should just move on and save the questions for the discussion. Can I ask you, Mathieu, to send us either a URL to your slides or the slides themselves?
Yes, There's already a slide deck which looks like this one, but I'll put this one particularly on the page, which is linked by the URL already.
Okay, so we already have it. Fantastic.